Ethernet is a family of wired computer networking technologies commonly utilized in local area networks, LANs, metropolitan area networks, MANs, and wide area networks, WANs. It was introduced commercially in 1980 and standardized in 1983 as IEEE 802.13. Over time, Ethernet has advanced to support higher bit rates, more nodes, and longer link distances while maintaining backward compatibility. Ethernet has largely replaced competing wired LAN technologies such as Token Ring, FTDI, and ArcNet. The evolution of Ethernet includes the shift from the original 10-base-5, utilizing thick coaxial cable, to the more cost-effective 10-base-2, which used a thinner and more flexible cable. Modern Ethernet variants make use of twisted pair and fiber optic links along with switches. The data transfer rates of Ethernet have increased from the initial 2.94 Mbit/s to the current 800 Gbit/s, with rates up to 1.6 Tbit/s in development. Ethernet standards encompass various wiring and signaling variants of the OSI physical layer, dividing data into frames containing source and destination addresses and error-checking data. Ethernet has a rich history originating from the design of AlohaNet in the late 1960s by Norman Abramson. The adaptation of the AlohaNet approach to shared coaxial cable transmission by Robert Metcalf and David Boggs at Xerox PARC led to the development of Ethernet in 1973. Ethernet enhanced communication by implementing carrier-sense multiple access collision detection, CSMA-CD, allowing for efficient data transmission. Standardization efforts from companies like DEC, Intel, and Xerox culminated in the Ethernet Blue Book in 1980. The development of Ethernet led to the founding of 3Com by Metcalf, driving further advancements in the technology. Ethernet's transition to twisted pair cables in the mid-1980s with StarLAN and later 10-base-T allowed for easier installation and increased reliability. The introduction of Ethernet switches in 1989, such as Motorola Codex's 6310 EtherSpan and Kalpana's EtherSwitch, revolutionized network communication by reducing latency and enabling collision-free transmission. Advanced networking features like shortest path bridging, SPB, and the Spanning Tree Protocol, STP, further enhanced Ethernet technology by providing robust security and scalability. Ethernet's evolution has positioned it as the dominant networking technology, offering high bandwidth, improved isolation of devices, and enhanced network reliability. The Ethernet physical layer has developed over an extensive period, encompassing various interfaces including coaxial, twisted pair, and fiber optic physical media interfaces, with speeds ranging from 1 Mbit/s to 400 Gbit/s. The first implementation of twisted pair CSMA-CD was through StarLAN, standardized as 802.3 1BS5. Although 1BS5 had limited market acceptance, it laid the foundation for the physical components carried over to subsequent technologies like 10-base-T through 10G-base-T. The most commonly used variants include 10-base-T, 100-base-TX, and 1000-base-T, utilizing twisted pair cables and 8P8C modular connectors to operate at 10 Mbit/s, 100 Mbit/s, and 1 Gbit/s, respectively. Additionally, fiber optic versions of Ethernet, often employing SFP modules, are prevalent in larger networks for their superior performance, improved electrical isolation, and longer reach. These variants can span tens of kilometers with certain versions, offering increased flexibility for network expansion. Generally, network protocol stack software operates similarly across all Ethernet types. In the realm of frame structure, within IEEE 802.3, a datagram is referred to as a packet or frame. The frame consists of the preamble, start frame delimiter, SFD, carrier extension, if applicable, frame header with source and destination MAC addresses, and the ether type field indicating either the payload protocol or payload length. The central section of the frame contains payload data, including potential headers for other protocols carried in the frame, followed by a 32-bit cyclic redundancy check to detect data corruption during transit. Auto-negotiation plays a critical role in Ethernet connections, enabling two connected devices to establish common transmission parameters such as speed and duplex mode, ensuring optimal communication. Initially introduced as optional with 100-base-TX, auto-negotiation became mandatory for 1000-base-T and higher speeds, enhancing compatibility and efficiency in network setups. Moreover, in the event of error conditions like a switching loop, Where multiple Layer 2 paths exist between endpoints, broadcast storms can occur, causing network congestion. To address this, it is essential to establish a loop-free logical topology using protocols like SPBE or STP, despite physical loops being appealing for redundancy. These measures prevent broadcast storms and ensure smooth network operation. Furthermore, jabbering, where a node excessively transmits data beyond the permitted window, poses network disruption risks. Detection and resolution methods vary based on the physical topology, with mechanisms like jabber timers on repeater hubs limiting transmission durations to maintain network integrity. Measures such as jabber detection by end nodes, timer-based intervention, and frame size enforcement contribute to efficient network management and error mitigation in Ethernet environments.